Hello everyone, my name is Artur Bille, and in this video I would like to present you the results of my cooperation with Professor Viktor Buchstaber from the Spectral Institute in Moscow, Russia, and Evgeny Spodarev from the Ulm University in Germany. All details and further results you can find in our article with the title Spectral Clustering of Combinatorial Fullerene Isomers based on their facet graph structure. What I want to present you here is, first I will explain you what a fullerene is and what mathematical model we use for it. Then I will explain briefly what an isomer of a fullerene is, and then based on this definition the question or the need of a clustering system arises naturally, and I want to present you some results of ours. And then I will give you an outlook what has to be done in the near future. So from a chemical point of view, fullerene is nothing else than a carbon molecule with n carbon atoms. Probably most of you have heard about graphene, which looks like a piece of paper. It's flat. In contrast to that, we have now a closed cage-like molecule which looks like a sphere. And as you can see in the picture, we have here 4 examples of fullerenes. The atoms are symbolized by green dots, and every atom is connected to exactly 3 other atoms by a yellow edge. And the sphere is subdivided into pentagons and hexagons only, where the number of pentagons, which can be easily be shown with mathematical arguments, that the number of pentagons has to be always equal 12, and the number of hexagons is always equal to n over 2 minus 10, where n is the number of atoms. And as you can see in these pictures already, we have fullerenes can have different shapes. We have 3 ball-like fullerenes and 1 tube-like. Also, if you take a closer look on these pictures, you will find out that in the ball-like fullerenes, the 12 pentagons are kind of uniformly distributed on the surface of a fullerene. In the tube-like fullerene, we have 2 poles, each consisting of 6 pentagons. So it's interesting that the distribution or the connectivity between pentagons and hexagons defines the shape of a fullerene. And this is the basic idea of our mathematical model. But first we can translate all these chemical properties into a mathematical language in the as follows. We define a fullerene as a 3 regular 3-dimensional convex polytopes where all of its facets are pentagons or hexagons only. And by a so-called Schlegel diagram, we can project this 3-dimensional polytope onto the 2-dimensional plane, and we will get a regular graph where all connectivity between vertices remains the same as in the original polytope. But as I said before, we are not very interested in the connectivity between vertices, but in the connectivity between the pentagons and hexagons. Therefore, we don't care about the direct graph, but we care about the dual graph. So in the dual graph, we will get 2 kinds of vertices. The blue colored one in this picture are of degree 5 because they represent the facets, the pentagons in the original fullerene, and the second kind of vertices have degree 6. They represent the hexagons. And in this context, we define isomers as fullerenes with the same number of atoms or hexagons, which are combinatorially non-equivalent. So the connectivity between the hexagons and pentagons is different. And having this definition, a question arises about the number of fullerenes for a given number of n. The exact formula for the number of isomers is not known, but some important properties are already derived. We can say that in this context it's important to say that the number of isomers grows like n to the power of 9. It's nice that it's not exponential but polynomial, but still it's growing very fast. For example, for C60 we have already 1812 isomers, and the question is, okay, we have a large amount of fullerenes, how to cluster them? Are there some similarities between some of them? And we derived the following idea. We don't care about the whole fullerene, we just care about the hexagonal subgraph, meaning that we care about the vertices of degree 6 only. We compute its adjacency matrix A, then we compute its kth power and sum up the diagonal and call it Newton polynomial, TK, or Newton polynomial. Based on this Newton polynomials, we can check how many different values for the Newton polynomials we get, and based on that we can clusterize all fullerenes. So the question then is, how many of these Newton polynomials do we really need? Here I would like to present one basic example. We consider this 1812 isomers of C60, and we use the single-step clusterization. In our paper we presented some other methods as well, but this is the easiest one. So for every atom we compute the Newton polynomial of degree k, and we check how many different values we get. And after 12 iterations, we have a complete clusterization of all isomers, meaning that every fullerene is uniquely characterized by T12, by the Newton polynomial of degree 12. And what is interesting now is, okay, you could ask, okay, this is a nice mathematical idea, but how is it connected to real world properties of a fullerene? So therefore we will consider the case k equal to 2, and we checked how many different classes of fullerenes we get and how many isomers are in these classes. So, and we found out that the two smallest and the three largest Newton polynomials have all just one single C60 isomer in this group. And therefore we checked them, why are they so special? And it turned out that the Newton polynomial are highly correlated with the relative energies of fullerenes, meaning that the smaller the Newton polynomial, the smaller the relative energy this isomer has, meaning that it's more stable. On the other side, the larger the trace, meaning the Newton polynomial, the higher the relative energy and the least stable this fullerene is. So we have already a nice real-world applicable way of clustering our isomers, and the question arises then, okay, if we want a complete clusterization, what is the largest degree of our Newton polynomial needed? If we consider not C60 but maybe C80 or C1000, what interesting isomers will arise then? And then finally, using these Newton polynomials, we want to establish an enumeration system for all fullerenes, not caring about the number of of atoms n. So this is what I wanted to present you in this video. I hope you are interested in this topic, and I'm very curious about your questions, your feedback, and maybe also further ideas. Thank you very much for your attention, and see you.